So I welcome you all to this next lecture in which we will be covering the topic related to the surface tension and the interfacial tension. So I have already discussed different effects to make you feel that why surface tension is important for different applications. So so here I have given you one question where we need to compare the surface area of the sphere with that of the cube. So we need to find. So let's solve this question. And I will give you the answer through this that why a liquid drop in a free media always tries to attain a spherical shape and not the cubical shape. Okay, so the volume of a sphere is V, so that is 4 upon 3 pi r cube, and volume of cube is V, that is also a cube. So from here the characteristic length comes out to be 3V by 4 pi to the power 1 by 3, and a comes out to be v to the power 1 by 3. So we need to calculate the surface area. Surface area of sphere is 4 pi r square, and surface area of cube is area of cube is 6a square. So here a we know, so it comes out to 6 v to the power 2 by 3, and it substitute r here. So 4 pi 3v to the power 4 pi to the power 2 by 3, and solve this, and you what we get is 1.36 1.36 v to the power 2 by 3. So from here we can prove that a sphere has a cube has having a higher surface area, and we have considered from this we can say that the shape of the sphere is like that. It has a minimum surface area, and surface tension is the force that surface tension. It is the force per unit area, force per unit length, or energy per unit area required to create a new surface area. To make you feel about the concept, so consider uh, in our childhood days we have seen that we have this kind of ring, we have this kind of ring. We drop in a soap solution. We drop that in a soap solution to make a bubbles out of it and makes a and we so when we dip this into this, what will happen? So there is a thin film form around this. So thin film form on this ring, and when you blow air with your mouth, this film detached, and as soon as this film detached from this sphere, a bubbles formed. And why the bubbles formed, and that are spherical in nature, and that is because of the surface tension of the liquid tries to make it spherical to attain a minimum surface area. You can do. There is one more experiment to see the effect of surface tension. So, so if you have this kind of system where you have a film of a soap solution on this ring, and you put some thread, some closed thread over there randomly. If you put this closed thread, then nothing will happen. This will sit over here, over this film, and nothing will happen. But if you prick it with a pin, if you prick it, Then after pricking, what will happen? After pricking, what will happen? Prick inside a thread with a needle. So what will happen? You will see this. So finally, what will happen? There is no, this random thread is like this. And what will, so there is air now. Here is the soap solution, the film. The surfactant film is there already. And what will happen? This thread, after some times, will become like this. This will attain a, this will attain a circular shape. So why this happens? This phenomenon also happen because of the surface tension. So what happens here is the surface tension acting here. So these molecules, these surface or this length. So it's in 2D, so that's why it's a length. So it wants to minimize this. So in order to minimize this, it will take a circular shape, and that is because of the surface tension. The surface tension make it this way, and this is the equilibrium attained, and this is the top solution. So all these effects are because of the surface tension. Even what I told you that this conversion, so why it becomes a sharp edge because of the surface tension. Minimize this surface area. Here all rises in cotton wick. That is because of the surface tension. We will discuss this phenomenon in detail. Mercury does not wet a glass water because it is hydrophobic to the surface, and those hydrophobicity and the wetting properties. Wetting is also defined with the help of surface tension. Okay, so that's about the surface tension. So to define a surface tension in a more classical manner, so we have taken a thin film in this ring. Consider a thin film in a ring. So I am hereby defining a surface tension in terms of force per unit length. Surface tension in force per unit length. Okay, so that's the film here, and let's put a put some let's draw some imaginary line here. AB. The surface on either side of the line exerts a pulling force on the surface on the other side. So here it tries to pull it here, the force in this direction and this force acting in this direction. So whatever, so this, so it's like a needle placed over a thin film of surfactant solution. So you have seen, you may see those experiments, and you can also try at home. You can, so that is the surface tension that makes it uh, put over a surface, and nothing is happening because of the force, because of these forces acting on this needle, such that it will remain in equilibrium state. And this, that force that is acting on this, that is the surface tension, and this tension is, we can define as S or sigma in general, that is force acting, that is normal to this and tangential to the surface per unit length of this needle. Okay, so that is force per unit length. I can edit this definition. So it is better to say energy per unit area if we are talking in terms of creating a new surface area. For a force per unit length, it is like this. The dimension of surface tension is, you can calculate, that is mlt minus 2 divided by L. So that comes out to be mt minus 2. That is Newton per meter. In general, surface tension of the surface tension of the liquid depends on the temperature of the liquid as well as on the medium on the other side of the surface. In a more generic way, if you see that there is a pool of water, there is a pool of water, and that is fluid here. So that's the free area, free surface. So the gamma is here is gamma. If it is a water and it is a here, so gamma is defined as the water here. So that is the interfacial tension. That's why we are calling this tension, that surface tension dependent upon the medium on the other side of the interface. Now, let's discuss the same surface tension in terms of energy per unit area. Surface energy. So that is energy per unit area. That is also surface tension, gamma, sigma, anything you can say. So if you see this example again, the top one. So let's say this is the interfacial area. Now, if you track this molecule, we need to go at the molecular level to understand this. So there are a lot of water molecules. So if you track this molecule, so that is this kind of cluster are all around. So these forces are basically can on this cancelling out each other. But if you track this molecule here, so it is something like this, 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 this. What will happen is you can see that almost half of the molecules were not there. Okay. So what will happen is, so now half of the molecules are not there. So there is some sort of a loss of energy to this, and there is a disbalance will be there, and there is some excess energy due to this interaction with the molecules of the air. So now it has an interaction that is balanced by this. So there's now if it is A interaction, now there is a creation of AB interaction. So this AB interaction creates a new surface area which requires some energy to maintain it, and that energy is basically the energy per unit area is called the surface tension in terms of energy. Okay, let's try to correlate the relation. Let's find out the relation between surface tension and work done in increasing surface area. Okay, so let us consider a bent of wire and that is dipped in a solution such that so this here we have a liquid film formed here. This force is acting in this direction. That is, so let a liquid film formed between a bent wire ABC and a straight wire PQ. So that is ABC, and there is the that we have put over this bent wire, that is PQ. This is straight wire. PQ, which can slide on the bent wire, which can slide on a bent wire without any friction. As the film surface tries to contract the wire PQ moves upward. So as the film apply a force in this direction, so this wire will move in this direction because of the surface tension. So to keep PQ in equilibrium, a uniform force F has to be applied in the downward direction. We don't want to move this, so we are applying a uniform force F in the downward direction, which includes the weight of the wire. So, or you can consider this wire to be massless, considering that wire is massless. And we found that F this force should be equals to the, so that is length, let's say length of the wire. So that comes out to be the, so in this direction, what is the force? That is surface tension. So that surface tension is acting to T into L that we have already discussed here. So that is T into L, or the S into L or gamma into L, whatever. That is, so that's the surface tension. So that is, let's take it as into L. But mind here, you are doing a mistake here because that's the soap film. And that, please keep it in mind that when there is a soap film has two surfaces very close to each other. If I'm writing this, so it means that it has this area. I'm considering what I'm looking at from my side. But at the back there is one more surface area of the soap film. Those two surface in general, soap film is a bit thick compared to the other films, and that is because that there are two films in contact with each other. So the correct way to write this force is two surfaces. So that is two length. So S into 2L, because there are two free surfaces. Okay. Now suppose wire moves delta x in downward direction. So if it is moved down in delta x in downward direction, let's say this is the x in downward direction. So the total increase in surface area is 12 into delta x. Okay, so the total increase in area is x into L, and that is for on the two sides, that is 12, 12 into delta x. So the work done in increasing this area is comes out to be, so let's call this L into delta x is equal to 2 into delta A. So it comes out to be S into 2 into, or you can take this 2 inside also, so that is delta A. So this is S into delta A. And from here you can get surface tension is work done in creating a new surface area. Work done per unit area. So surface tension, I already told about this above. The surface tension is can be defined as the work done in increasing the surface area by unity will be equal to the surface tension. Okay, so take one question related to all these concepts. So we have considered this kind of soap film here, and we have this rod there, that is sliding rod. This is the film A, B, C, D, and this is PQ, that is that you can slide. You can slide this wire. Okay, so that is there, and you put a some small amount of weight mg. Surface tension of soap film is 0.03 Newton per meter. Length is 10 centimeter. So we need to find out the mass of this block. The mass of this block that is attached, in order to find out the mass attached to the mass tied to the string PQ, such that it will remain in equilibrium. So try to solve this issue. Okay. So to maintain, so whenever we say equilibrium, so F net on PQ should be zero. Okay. So the force acting here, this force is due to the surface tension. So force due to surface tension is equals to the weight attached to the spring. So the force acting in this direction, that is F, should be equals to mg, and this forces, because I told you it's a circle. So again, don't do that mistake again. So F is 2 s L is equals to mg. We need to find M. 2 s L divided by g. So 2 into 0.03 into length is 10 centimeter. 10 into 10 to the minus 2 divided by 10. So what we get is 6 into 10 to the minus 4 kg, or 0.6 gram. Okay. 0.6 gram of weight is needed to balance this. Now let's look at another concept, that is excess pressure. Pressure inside a liquid droplet. So let us consider a drop of radius r, assuming, or I will write completely. So let us consider a spherical drop of radius r. If the drop is small, the effect of gravity, the effect of gravity can be neglected, and shape is assumed to be spherical. So if it is P2, if it is P1, then P2 minus P1 comes out to be 2T by R. So we can derive this. So let's consider that we cut this bubble in a way that so let's cut this bubble so it will become like this. So we have sort of a hemispherical cap. Consider this as we have a sort of a spherical cap, and this here we have a force that is due to the surface tension that is acting on the periphery. So this pressure is so considering this area. One minute. So here we have this force that is acting that is due to the surface tension, and this is if you consider this as a periphery, then this force is nothing but 2 pi r into the surface tension, that is P, or I am taking S. So the excess pressure comes out to be P into area, that is pi r square is equals to 2 pi r into S. So excess pressure is nothing but, so P excess is 2T by r. Okay, so this is the excess pressure inside it, and this excess pressure is this. So P excess is P2 minus P1, that is there. But if it is a soap bubble, then P excess is 4T by R, because now this film is having a two surface, one is outside and one is inside. So it will be something like this. So it has two areas, and that's why we have we should take two uh, twice of the perimeter, and so what we get is P excess is 40 by R for a soap bubble. So that should be take care. So we have some time to discuss the contact angle. You can also find out uh, this excess pressure with the help of the work done in expanding a bubble. So I'm not taking that because the formula is important for you. Or or I can take it. Just briefly going through it. So if we have this, so we have this uh, surface, we have this bubble, and let's say you are expanding it to, if this is at the radius r and this thickness is delta r, so the work done of expansion is, so 4 pi r, because it's the surface area, because now we are looking at the work done, so that is r plus delta r square minus 4 pi r square into surface tension, that is liquid air surface tension. This should be equals to 8 pi r delta r into liquid air surface tension. So that is nothing but 4 pi r into delta r. So we have taken the differential area, this differential area of expansion. So if it is 4 pi r square, so the change in area comes out to be with r, if, so ds by dr comes out. So if it is s, so ds by dr is 8 pi r, and so ds is the change in surface area is 8 pi r dr. That's why we put it like this, that is delta r. And we find, so that is for the case when it is in equilibrium, and the work done due to pressure is P inside minus P outside into 4 pi r square into delta r. So using this two equation, balancing this, putting this delta r, what we get is Pi minus P naught, should V comes out to be 2s by r. Okay. And similarly for the case of bubble, it is Pi minus P naught is equals to 4s by r. In the next class, I will be discussing about the uh, capillary rise, contact angle, and previous year JE questions. With this, we will be going to wrap up the fluid mechanics. Okay.